Okay, good morning, 11th grade. I hope you guys are doing well this morning. I'm going to be very honest with you. I am tired of virtual learning. I miss you guys. I wish you guys were here in the classroom. I wish we could do things hands-on and get more involved with what we're talking about and what we're studying at this point in time. But unfortunately, sometimes life happens and you just got to roll with the punches. So here we are. Anyway, I hope you guys have been doing well, that you've been keeping up with your notes, because I am going to be checking them. Eventually, somehow, some way, I will be checking them, so please make sure that you are keeping up with them, because they are going to count for a quiz grade, alright? We're going to start a new chapter today. We're going to start studying nuclear chemistry, okay? I know you can't see that title very well in this color, but this color you can see the rest of the notes on well, so that's why I picked it. But the title here is Nuclear Chemistry, and it's obviously chapter 17. There you go. So, radioactivity. What does it mean if something's radioactive? That's what we're going to look at. So, oh, excuse me. Whew. I apologize. Nuclear chemistry is the study of reactions involving the nucleus. Now, nuclear chemistry became very popular towards the end of the 1800s into the early 1900s. And scientists like Henry Becquerel, Pierre and Marie Curie were fascinated. This is supposed to say were, not we. Sorry, my bad. It's early. Sorry guys, it's early. Were fascinated with the phenomenon of radioactivity in the late 1800s and early 1900s. Pierre and Marie Curie were so dedicated to it that Marie Curie actually died from radiation poisoning because she exposed herself to it regularly, because she was so intrigued by it and so enthralled by it. The first controlled self-sustaining nuclear chain reaction was conducted by an Italian physicist named Enrico Fermi in December of 1942. This nuclear chain reaction that he had controlled and had formulated to be self-containing, this would actually lead to the formation of the nuclear bomb and really nuclear warfare as we know it today. So what is radioactivity? Now, the nucleus of the atom is composed of protons and neutrons. That's nothing new to you. We've talked about that pretty regularly throughout the school year. But the total number of protons and neutrons is known as the mass number. Now, we did talk about that all the way back in the first semester, so try to jog your memory a little bit. The mass number is the total amount of protons and neutrons in an atom, okay? And in a balanced atom, it's an equal number of protons and neutrons. Atoms of the same element that have different mass numbers are known as isotopes. So you can have the same element but different mass numbers, because some elements, some isotopes, because that's what they are, okay? Some isotopes might have a mass number of 238, where others might have a mass number of 200, all right? So it can still be the same element, but they can have different mass numbers, and when they have different mass numbers, they're known as isotopes. That's going to be important to remember, so tuck that back in your brain, okay? The best example of this that I can think of in relation to nuclear chemistry is the element uranium, okay? Uranium can have tons of different isotopes. It isn't just the form of uranium that you see on the periodic table. Now, stable versus unstable. Something that is stable means that it shows no tendency to break up or suddenly change into another element, okay? If it is stable, it typically has equal numbers of protons, neutrons, and electrons. It is not looking to get rid of electrons, like we've talked about other elements. They seek to easily get rid of electrons. It's not necessarily looking to get rid of electrons. It's not looking to gain electrons or even gain protons from another element. All right, stable elements, they are happy elements, okay? The best example of stable elements would be the last column of the periodic table there. Those are all very stable elements. Something that is unstable, it has the tendency to spontaneously shed subatomic particles, those subatomic particles being your protons, neutrons, or electrons, or break apart due to protons and neutrons being loosely held together. Now, in some elements, your protons and neutrons are not tightly bound together at the core of the atom, okay? Some of them, it's more like, for a stable atom, okay, let's do it this way. For a stable atom, it is tightly interlocked, okay? Like if you made a fist, put your fingers together, you were holding your own hand, okay, it's tightly interlocked. Those protons and neutrons are not going to seek to be loosed of one another. Versus an unstable atom, those protons and neutrons have a little bit more space between them. They're still connected, okay, I don't know if you can see my hands very well here. They're still connected, all right, but you see there's space in between them, okay? And because there's space in between them, that means, hey, maybe I'll let go of this proton I'm holding on to eventually, okay? So something that is radioactive, because that's what we're going to be dealing with for the majority of this chapter, is radioactivity. And the results of radioactivity anyway. So something that is radioactive, this is the tendency of an unstable substance, okay? So it either has the ability to spontaneously shed electrons, protons, or neutrons, or those protons and neutrons are loosely held together. So it's a tendency of an unstable substance to undergo nuclear decay and emit nuclear radiation. So radioactivity is the energy release or nuclear radiation from unstable elements and isotopes. So something is radioactive, it has the potential to release this nuclear radiation, this nuclear energy. When it has actually reached the point that it is releasing the nuclear radiation, that's what we call radioactivity, okay? Now, nuclear radiation are the particles and electromagnetic waves produced by nuclear reactions, okay? So they're all radioactive, radioactivity, and nuclear radiation, they're all related to one another, okay? That's why I did the definitions boom, 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 one right after another, because they're all related to one another. And it can only happen if something is unstable to begin with, hence why we talked about stable versus unstable. Sorry, I need a drink, guys. All right, a nuclide. Oops. Just pretend you didn't see that. A nuclide is a specific type of atom described by both its atomic number and mass number. Any isotope of any element is considered a nuclide. So think back to when we were talking about isotopes there a minute ago. All right. An isotope is two of the same element, but they have different mass numbers. Another name for this is a nuclide. All right, nuclear stability. I'm gonna grab my water, sorry guys. It's a very unprofessional video today. But that's okay, because it's Monday morning. Sometimes Mondays happen. Anyway, here we go. We'll try to get more professional for the rest of this video. Nuclear stability. We are gonna go ahead and do 2 Roman numerals for this week's notes, just because I'm trying to finish the chapter before the school year ends, trying to stay on track with doing the 1 video a week like I've been giving you guys. And in order to do that, we gotta have 2 notes today. So 2 sections of notes today. So it is gonna be a longer notes video, but you have a week to watch it. So nuclear stability. Now, the stability of any atom is determined by the number and arrangement of protons and neutrons in its nucleus, okay? The more even the number of protons and neutrons, the more stable the element is, okay? If you have 4 and 4, then it is considered stable. If you have 4 and 3, well, you're getting more unstable there. If you have 4 and 2, even more unstable, all right? Now, about 99.97% of an atom's mass is contained in the nucleus, okay? So the majority of the mass of an element is found in the nucleus of that atom. Hence why when nuclear explosions happen, they are so powerful, because you have so much mass being broken apart in a very, very short time. All right, the nuclear force. Now, 2 protons in close proximity to each other will repel each other Because they are both positively charged. That just makes sense, okay? You've learned before in science, and I'm pretty sure we've talked about it at some point in time this school year, where opposites attract and likes repel, okay? So if two positively charged items get together, they're going to push against each other. They're going to push away from each other. They're not going to come together, right? So you don't have to write these dashes down. These are just thought to help me continue with my thought process, all right? You can write them down if you want, but you don't have to. So what holds the nucleus together if protons repel each other? Why does it stay together if these protons are pushing against each other all the time? Because they don't want to be next to each other. So the strong nuclear force, this is what binds this atom together. It's what keeps those protons from pushing against each other all the time. Okay, sorry, I had a little bit of a brain blank there. The strong nuclear force. This is the force that acts on protons and neutrons and binds them to the nucleus. This force is 100 times stronger than the electromagnetic force by which protons repel each other. So you have the strong nuclear force. If you think back to 9th grade science, we did very, very, very briefly talk about the strong nuclear force. But we didn't talk really about, we pretty much just defined it. We didn't talk about why it works or anything like that. So you have the electromagnetic force, which states that opposites attract and likes repel, right? But you have this strong nuclear force, which is 100 times more powerful than this basic opposites attract, likes repel principle, okay? So this strong nuclear force comes into play and it overcomes that repulsion and pretty much pushes the protons together with the neutrons so that they bind together to create that nucleus of the atom. Now, radioactive decay is the conversion of one nuclide into another in a spontaneous nuclear reaction. Did I go past what did I click too far? No, I didn't. Sorry. Again, guys, it's Monday. I apologize. We're just gonna roll with it, all right? Anyway, radioactive decay. This is the conversion of one nuclide into another in a spontaneous nuclear reaction. This is almost always accompanied by the emission of nuclear radiation. So when one nuclide gets transforms into another in a spontaneous nuclear reaction, so let's break it down. What are we talking about here? When a isotope, okay, when an isotope kicks out a proton, okay, it converts into another isotope, right? If it kicks out 5 or 6 protons, it converts into another isotope. So that's what radioactive decay is. It is as an element or as an isotope kicks out protons, it goes down a level to create another isotope, all right? But as it kicks out that proton, right, it's kicking it out, doesn't want it anymore, it creates this nuclear radiation emission, okay, because it's got to have a lot of power to overcome that strong nuclear force, number one. But number two, it also has, the proton itself has some power behind it. So as it's kicking out those protons, it's emitting a pretty powerful form of radiation. The nuclear mass effect. This is the mass of every atom being measurably less than the total mass of its individual particles. Now, how do we account for this missing mass? The theory of relativity, okay? So, as they were studying, right, they realized, okay, the overall mass of an atom, it's actually less than if we were to measure the particles of every, if we were to measure all the particles that compose that atom, right? So, how do we account for this? Well, that's where Mr. Einstein comes in and his theories of relativity. Now, the theory of relativity mathematically expresses that energy has mass, E equals mc squared. It's probably one of the things Einstein is most famous for, right? So, because energy has mass, okay, the fact that the atom itself has energy, that energy that the atom contains has mass, all right? The mass that is lost because of nuclear mass defect is found in the energy released by the atom. So, because energy has been lost, the energy that is found makes up that difference, okay? So as it kicks out energy, wherever that energy has gone into picks up, the object that energy has gone into picks up that energy. So the energy isn't destroyed, because remember, matter and energy can't be created nor destroyed, they just change forms or they absorb into something else, okay? So this is how we account for the missing energy and the missing mass. The law of conservation of matter and energy, I just stated it for you. Matter and energy can neither be created nor destroyed. They can only change forms. Sorry, well, this works. They can only change from one form to another. And the nuclear binding energy, the mass defect is also equal in magnitude to the energy required to separate a nucleus into its individual subatomic particles. This excuse me. This works hand in hand with the nuclear binding energy, which is the amount of energy necessary to break up a nucleus into its component nucleons. Okay, and remember, if you remember back to the beginning of the school year, nucleons are just another term for the protons, neutrons, and electrons of an atom. All right. A nucleus must have less energy than the individual component nucleons. Okay. The energy difference between the two is equal to the binding energy. The electron volt, or the EV, this is the kinetic energy gained by an electron when it is accelerated through 1 volt of electrical potential. Now, this matters because of radioactive radioactive plants, nuclear plants. There we go. Sorry, guys. Nuclear reactions are measured in mega electron volts, MeV. All right, one atomic mass unit is equal to 931.5 mega electric volts. So one loss, okay, one loss of a proton in an atom is equal to that 931.5 mega electron volts, which is a lot of energy if you stop and think about it. That's enough to fry just about anything or anyone. Binding energy per nucleon, this is found by dividing the binding energy by the number of nucleons in the nucleus. We're not going to do the math because you guys aren't here to learn the math, and I don't want to necessarily teach it over video and confuse you all. But it's basic division for the most part. The higher the binding energy per nucleon, the more strongly the nucleus is held together. That just makes sense. The more binding energy, the stronger, the more tightly it's going to be held together. This means that more energy is required to separate the individual nucleons. Again, just makes sense, guys. Logical thought process there. The more you have, the more it takes to break it apart. And that's where we're going to stop. Okay? So, familiarize yourself with radioactivity, because next week when we talk about nuclear reactions, we're going to be referring back to these terms, so make sure that you have gotten them down. I hope you guys have a good week. I am praying for you, and I hope to see you soon.